Okay, so today is the chain rule, and I'm going to show you how you take the derivative of a function inside a function. Now, it might not seem that practical, but you're going to see there's lots of examples of this when we start going. But the way it works is it's the derivative of the outside. So the outside function is f times the derivative of the inside. So this is our last differentiation rule for a little while here. But again, it is one of those that you are going to be expected to know and use quite a bit. So let me show you why it is that it doesn't turn out to be, or that it does turn out the way it is here. I'm going to use this definition of derivative. So all I've done is use the composition of the two functions. And the step here to getting through this proof, this is sort of the genius step. The rest of it falls into place after this, is this hint that I've given you. If you multiply on the top and bottom like this, I'm multiplying by 1, so I haven't actually changed the limit. So the way I'm going to rearrange it then is this will be the limit as x goes to c. And the pieces I want to pull apart, if I had an x minus c on the bottom here, this would just be the derivative of g. So I'm going to actually end up swapping these two products. So it'll look like this when I rewrite it. F of g of x minus f of g of c, and g of x minus g of c. Now this piece here is the derivative of f if I was to evaluate it at g of c. So instead of just at plain x, it's the g of x here. So this would be the definition of the derivative of f at g of x. Sorry, for us it's c. And this is just the regular definition of derivative that we worked with before. So it would just be g prime of c. So that's where that pattern comes from. It's much easier to use than it is to prove, of course, but you need some exposure, right, to doing proofs? Well, you might not feel like you need exposure to proofs, but you're going to get it. So for now, I just want to help you find the chain rule, and the way you think about it is an inside and an outside function. So inside, because it's inside the brackets, so on the original one, this is the inside function. It's inside the brackets, right, the innermost function. And this would be the outside function here, f. So let's go through and try and pick out the pieces. If we were working on this one, what would let's go with the inside function. What would the inside function be? Oh, yeah, you've actually jumped all the way to the derivative. All I was hoping for was the inside function. Before we can do derivatives, we have to be able to pull them apart. So 3x squared plus 1. What's the outside function? Yeah, the power 7, so to the exponent 7. But I like to write it like this to remind myself that how I'm going to be using it. So here's, if I'm going to do chain rule, it's going to be the derivative of the outside function, which is just the 7th power. So I use power rule. 7 times this to the 6th. Okay. So we can forget about that mess inside, and we can just treat it like it was power rule. But however, we have to multiply by the derivative of the inside, which is 6x. So the derivative of this piece here, the only technique you'd have to do this right now would be to expand it, and that's quite a long process with the 7th exponent. But now you have a technique that will give you the derivative here without having to do all that. Okay, how about the next one? 3x plus 5 and 2x plus 3, or sorry, to the 2/3. What would you end up with then? So let's pick the easy way. Let's pick the inside function. Yeah, x plus 5 is the inside. And the one I'm thinking of that I have to still tend to looks like this. So then when I look at the outside function, it's just power rule again. So 2/3 times 3, that'll be 2. And it'll be a negative 1/3 once I subtract 1. And the derivative of x plus 5, that's just 1. So for the next one, it's not obvious how this is a chain rule question. Can anybody, maybe you can see it? Anybody see it? Yeah, it takes some practice. It's okay. Yeah, so if I just rewrite it this way, now I have an inside function, x plus 1, and the exponent is negative 1 and I'm using. So I'd be thinking about this problem like this. Here's my outside function. Here's my inside function. So the derivative of the outside is negative 1 times the inside to the negative 2. And again, I just have 1 here for the derivative of x plus 1. Okay, so we'll do the last one and then I'll let you try a couple on your own. If I was to use this, the outside function I'd be dealing with is the square root graph. However, square root's not that explicit in terms of what it does. So it's probably better that you think about it as to the 1/2 so that you can use the power rule. The inside function here would be 3x squared minus x plus 1. So the derivative of the outside will be 1/2 3x squared minus x plus 1. And then after I subtract 1, it'll be negative 1/2. And the derivative is 6x minus 1 of the inside. Okay, so you have a bit of a template there. I know it's very foreign and new, so what I'd like you to do is try doing these next 3, see if you and your neighbor agree on what your answers are and what you came up with. Okay, so it looks like some of you are getting the hang of this pretty quickly. Here's what you should have for the first one. The second one, you can think of that as x squared minus 1, and it's being squared and the cube root, so that would be the exponent is 2/3. So if I did the chain rule here, the derivative is going to be 2/3 x squared minus 1, and I subtract 1 times the derivative of the inside, which is 2x. So I could write that as 4x over 3 times x squared minus 1 to the negative 1/3. The last one, if you rewrite it like this, you could do a quotient rule on it, but it's not necessary. If we rewrite it like that, 7 is just a constant. It won't affect this. We just multiply through by the constant. So now we only have to do a chain rule question. We don't have to do quotient and chain. So this will be, when I multiply by negative 2, it'll become 14. 2t minus 3, subtract 1, and the derivative of the inside is 2. So I would have 28 times 2t minus 3 to the negative 3. So the only other thing that we can work out here is, before we jump right in and use our techniques, we may wish to simplify. So for example, this one here, instead of doing x squared times the root, I would have a product rule here, and I'd have a chain rule here. You'd have two different, it's not that it's not within your reach, it's just, let's make life a little easier. How could I move this product inside that other function there? Yeah, so it would end up being x to the 4 on the inside. So what I'm going to end up with here is x to the 4 minus x to the 6. Now it'll just be a chain rule that I'm working on. So I have 1/2 x to the 4 minus x to the 6th. Take 1 away. And the derivative of the inside is 4x cubed minus 6x to the 5th. Now that one could be simplified. For example, this multiplication by 1/2 could take out the 4 and the 6 to 2 and 3. And I could also move this square root to the bottom. But for now, I'm happy if you're just able to do that. We'll worry about simplifying more when we practice later. Okay, what about the next one here? Well, what would you prefer to do? Quotient rule or product rule? Product? So product rule, you could rewrite this question so that it looked like this. To the negative 1/3. It is also possible to move that x inside. However, I think we'll leave it here and try a product quotient rule combination. Okay, we'll see if you're up for it. So I'll give you just a couple minutes head start. See if you can do the combination of both product rule and chain rule here. So it is quite messy, but that should be what you have for your product rule. And we could tidy that up a little bit, I suppose. I'm going to write it as, just to show you how it could be simplified, it's probably good that we practice one together. So this is 1 over the cube root of x squared plus 4. And over here, I've got 2/3. So I'm going to have 2x over 3 times, this will be the cube root again, x squared plus 4, and that'll be to the 4. We could, you know what, let's leave it as an exponent instead of a root. Just it's kind of crammed in and messy there. So to the 4/3. So we can also make a common denominator here. So to do that, I'd have to multiply this piece by 3. I need a 3 there, as well as an x squared plus 4. So the common denominator, I'll multiply this through. That way the bottom here will have the same exponent. So that just leaves me with, whoops, with these pieces. Sorry about that. Plus 2x. And then on the bottom there's 3x squared plus 4 to the 4/3. I think we'd be pretty happy there. I don't think I would want to go any further on simplifying. However, the times when simplifying is going to be, make life better for us is when we're considering a second derivative. It'd be easier to take a second derivative here now that you've done some simplification than to do the second derivative where we were back there. Because in this one, you've got two pieces to work on, and you still have a quotient rule here, so it didn't, this is certainly not making life any easier to do all of this compared to one here, which is going to be a quotient rule. Neither would be very, nice to deal with, but it would be better to deal with the last form here for the second derivative. Okay, so what about the last one? I'll let you guys see if you can work on the last chain rule question here. Okay, we could keep playing around with this, but that's enough. Here's the original derivative. Basically, it would be stopped here. But then I tried playing around a little bit to see if it would simplify. And I guess I'm going to say I'm giving up now. So that's, with the rules we've done, having a chain rule that combines the quotient rule, that's probably the worst of the rules that we've had, and both at the same time. So if you can handle that, you're in really good shape. For now, we're going to get a little bit of practice in, and we will continue our chain rule discussion next day.